Thanks, Joe. So it's a pleasure to be here, sort of for two ulterior motives besides the main reason to talk. One is it's always good to see my friend Kim. Kim and I talk in a variety of different venues, and so it's good for us to talk back to back. And more importantly, and I think more troubling for me, in thinking about talking to students, so I was actually a graduate student at Los Alamos, and so I've been doing sort of this time of year a number of student welcomes to the lab, and what I realized was I've spent exactly half my life since I was a graduate student fellow. So I first came to Los Alamos in 1990. So a number of you weren't even born when I started as a graduate student at Los Alamos. It was a bit troubling from point of age. But nonetheless, welcome. It's an exciting program. We certainly look forward to your successes going forward and hear about yourself for the next couple of days. What I want to do is talk about three things. I want to briefly give you an overview of the laboratory, just a few things we're thinking about. And the subtext for that part of the talk is, as Daryl introduced me, I'm pretty much a hardcore experimentalist who makes stuff. And so you can ask the question, what's a guy like that doing running a theory, simulation, and computation organization? And as I've noted in this new role, about half the theorists are excited to have an experimentalist in charge, and about half of them are terrified. And I think they're all right. And so we'll talk about that a little bit in the context of the laboratory. And then what I really want to focus on is two things. An effort we've been involved in the Office of Sciences, Office of Basic Energy Science, focused on mesoscale science, which I'll give you a flavor of as an important direction where I think materials research is going writ large across the nation. And then at least from our perspective, talk about a facility called MaRIE. MaRIE stands for Matter, Radiation, Interaction, and Extremes. It's Los Alamos' vision for what LANSCE becomes sort of in the 21st century. And so I tell you the story correctly, hopefully what I'll convince you is the broader science opportunity that's captured in Mesoscale plays out in the context of NNSA in an instantiation like MaRIE. And hopefully that's sort of illuminating in the broader context of the kind of work that you're all doing. And obviously don't hesitate to interrupt and ask questions as we go along. So why does Los Alamos exist? Our mission is clear. It's exactly the mission that Kim just described. Job one is to steward the nuclear stockpile. But there also are a broader set of challenges that we need to be responsive to. And importantly, energy security is one of those challenges as well. So we need to deliver on those missions. And we're entirely convinced that the way to do that is through science. So our goal is to be the premier national security science. When we deliver science for national security, we're being successful. When we lose track of that, we've lost our way. And so that's our focus. And what I want to do is give you a flavor of how we think about that. And the way we think about that is in the context of capabilities. One of the challenges we face is that mission challenges evolve, the things that we're responding to evolve. Nevertheless, there are a set of scientific disciplines very much consistent with the disciplines in which all of you work, in which we think we have to lead in order to be successful to deliver the mission. And so the mission challenges may evolve over time, but our need to lead in certain capability areas is completely invariant as a function of time. And so if we're good in those areas, then the mission will take care of itself. And so what we've concluded is that there are three areas in which we have to lead. One is materials for the future. And this is a bit code because the full description of this is experimental sciences focused on the future. And so that's, for example, where our work in HED is very much captured in that same space. And so this sector sort of spans 2/3 of all of you. I'll talk a bit about information science technology for prediction, and I will assert that the synergy between these two areas really is where the frontier of success is and is focused on why we're doing the set of things we're doing. And then conveniently, my colleague Scott Gibbs will talk to you tomorrow morning about the science of signatures. And the science of signatures, just as Kim noted, is exactly where sort of our interest in all things nuclear come to the fore. And the focus there is very much not just how do you figure out what happened after something bad happened, which is one aspect of science of signatures, but also much more importantly, how do you in an anticipatory way think about sort of measurement science and the set of things you want to think about before anything ever happens to be sort of significant in that way. And so we think that we need to lead in those three areas to sort of deliver on our mission here. And so us fostering the workforce of the future in these areas is sort of exactly why we exist. And that's why programs like this are so important to us. So I want to drill down a bit on materials. And so we've thought hard about what leadership in materials means. And what we think it means is that our vision is to achieve controlled functionality. And so people for a long time have talked about materials by design, and the notion that you can sort of go to the chalkboard or go to your computer and define a material and say that's what it's going to be. And that vision is probably a bit overstated. Nonetheless, I think we're at a place where we can actually think pretty carefully about the function we're trying to achieve and actually control that. And I would argue that many people, many places who think about leadership in materials would argue that their vision is something along these directions. So that's what success looks like. And in particular, there's a transition that we'll talk about when we come to MaRIE that historically the way we've thought about materials is largely in the space of observation and validation. Somebody makes something, we do some measurements, we throw it over the fence to our theoretical colleagues, maybe give us a model that can explain it, and it's iterative but not very effective. On the other hand, there's an opportunity to make a transition from observation and validation to prediction and control that makes that much more seamless and allows that to be possible. And from our perspective at Los Alamos, that overall vision plays out in three specific areas. The areas of defects and interfaces, the recognition that the materials that we care about are not pristine, perfect single crystals. They're actually relatively grungy, relatively dirty, relatively complicated things. And that complexity is what gives rise to their function. And so you have to understand and control the defects and interfaces that are intrinsic to materials if you want to achieve the functionality you want. The second of those is we need to do that not only in relatively ambient conditions, but also in extreme environments. So the environments in which we care about are rather extreme, both in terms of dynamic loading as well as the radiation extremes. That actually makes the challenge of controlled functionality even more extreme. And then finally, the question of emergent phenomena. The fact that materials display properties that you wouldn't otherwise predict from first principles, and that's what makes them cool and interesting and also allows them to deliver that function. So certainly, materials like plutonium display all of those properties, but so do a broad set of things. And so we think in the domain of materials, if we lead in these areas with a focus on controlled functionality, we're delivering for the mission. And so that's an important part of where we need to be focused on going forward. And we very much do that in partnership both with our sister laboratories and the broader academic community. So why is an experimentalist running a theoretical and computational organization? That's because our means of getting that done, our means of delivering on the mission in terms of delivering capability is focused on something called co-design. So co-design is relatively speaking a term of art in the computational science community where the recognition is we need to simultaneously design both the hardware in which we're running codes and the software in which we're executing them. And if you sort of say, I've got a code that might actually work on this machine or not, that's relatively non-efficient. But if you're sort of simultaneously thinking about hardware and software together, you can be successful in that space. And that's the traditional definition of co-design. We've sort of taken that a step farther and said, let's think about that more broadly. Let's think about how high-performance computing and simulation interact sort of seamlessly with theory modeling and simulation as well as data. Now, in some sense, that's just the scientific method, right? You take some data, you have a model, maybe you use a computer to simulate it. But I think the reason we focus on co-design is that being overt about how those things are coupled actually allows you and causes you to make progress more rapidly. And there's nothing like sort of asserting that our sort of theme is co-design to see that almost everyone who writes proposals at the lab now uses co-design in their proposals. And while that's just a proposal writing thing, it's not only changing what they write, it's actually changing how they think. And if we can do that more effectively, we can actually be successful in our mission. And so in some sense, it's a deliberate vocabulary trick to force people to think in a more integrated way, and that's something we're very much focused on. So I want to talk about co-design in two particular contexts. One is this context of mesoscale science. And so this is an effort that's led at the Office of Basic Energy Sciences in DOE by myself and George Crabtree, a colleague at Argonne. And the reason I show you this page is to point you to a report that was published by the Office of Science late last year and an article in the MRS Bulletin that was published sort of November of last year. So you can read those things if you want to. The slides that I'll show you here are relatively speaking official DOE slides. And so the way you'll know the difference between my slides and sort of their slides is green legend means their slides. And so that sort of points you in that direction. I want to give you a flavor of what that opportunity is. So the idea is that there's an opportunity to think about materials and how we achieve things like controlled functionality by thinking about materials at the mesoscale. So one needs to start with a definition. So clearly, there is a limit when things are relatively simple and relatively quantum mechanical and relatively isolated. So think about a single atom in a single box and how that behaves. And its characteristics are the ones shown here. And as we'll describe in a moment, that's relatively speaking a large success of the large push in nanoscale science over the last decade. We've done a remarkably good job of understanding materials increasingly at an atomic scale. Now, on the other hand, the materials we know and use in the real world are much more sort of bulk and have characteristic properties that are classical and involve the collective interaction of complexities that give rise to that. And so there's a recognition there's something in the middle. That thing in the middle is called meso. And so the focus in sort of mesoscale science is how do you translate the insights we have here into overall performance that plays out on those scales. And the assertion that that's not just sort of a simple continuation, that there are interesting properties that emerge in that space that are neither quantum nor classical, and that the opportunity is to translate from the quantum to the classical. And that's what we want to talk about. So importantly, that's not in any sense a declaration of victory that we know everything we need to know about the atomic scale, or that sort of nanoscale science is done. There's a variety of important things that still need to be worked on. And a way to think about it is sort of shown here. So over the last decade or so, over the last decades, we've sort of been in the materials community on a reductionist march, where we've tried to understand how materials behave on increasingly smaller and smaller scales till we get to sort of the scale that's just sort of dominated by quantum effects that focus on chemical bonds and perfect periodic lattices. And there's a very large area of activity in this domain at the moment. But it's also the case that our success in sort of marching down in this reductionist way enables a constructionist rise back up. How do we profit from the things we understand on these scales to understand a larger scale of phenomena, which actually push us harder to understand what are the nature of the building blocks that allow us to achieve the kinds of functionality we're talking about here. And so this translation sort of through reductionism up through constructionism sort of defines what the nature of the challenge is and gets to sort of what the heart of mesoscale science is. So in a longer talk, and you can certainly read about it in the report I talked about, the community has analyzed in some depth what the nature of mesoscale science is. And in particular, that there are these sort of 6 particular hallmarks that get to, so on the atomic scale, atomic granularity is very important. You can actually count sort of atom by atom how things are behaving. That becomes increasingly less important as you get to the mesoscale. Similarly, sort of the quantization of energy and sort of the domain of quantum mechanics dominates on the atomic scale, becomes much less true as you move through the mesoscale to the continuum. And on the other hand, what begins to dominate are the role of collective behavior. So the collective interaction of individual atoms doing things as a group that they wouldn't otherwise do individually. And there are multiple degrees of freedom interacting simultaneously. And it's these effects that begin to dominate and give rise to a hierarchy of structures where it really isn't a question of what's the character of the perfect lattice or the perfect chemical bond, but rather a set of mesoscale architectures that derive from that take advantage of the defects one's thinking about, not to be bad things, but actually good things that give rise to higher performance. So that's the domain of the science, and we'll talk about that a bit more. But I would say equally importantly is sort of how you do that science. One important aspect is that nobody gets a PhD in mesoscale science. And if you ask, is it materials, is it chemistry, is it physics, the only credible answer is yes. And so from sort of a sociological point of view, we have to think about how we bring communities together to do that science going forward. And also, as I'll describe, the tools that we've developed to do the kind of science we're talking about here tend to be relatively singularly focused on achieving ultimate resolution. And the opportunity really is, how do you do a multiplicity of measurements focused on appropriate spatial dynamic resolution where the measurements you're trying to do really are very much in situ. Understanding how the material is behaving is very much a key part of the mesoscale challenge. So I'll try to give you a flavor of that as we go forward. So I've tried to motivate why, that there are important questions that need to be addressed. It's also reasonable to ask the question, why is this moment in time a good moment to think about mesoscale science? And so part of that is we've actually built a pretty strong foundation, both of understanding and capabilities that allow us to tackle this problem. Sort of where we are in computational modeling is literally orders of magnitude more advanced than we were just a decade ago. So we have the computational tools that allow us to do simulations that are large enough and extend long enough in time that we can actually address these mesoscale questions. The set of tools and understanding we've built on the nanoscale over the last decade is truly remarkable. We can do things today that you really couldn't have imagined 20 years ago. And that's fortunate because the materials we're interested in are vastly more complicated and demand these kinds of capabilities. So it's entirely routine to think about chemical compounds that have 3 or 4 or 5 elements in them. We're not talking about what does perfect silicon do. Perfect silicon has an important role to play, but the materials we're trying to understand are much more complicated in that regard. And so it's sort of those elements and the progress we've made that allow us to take on that challenge. So let's try to be a little bit more specific and talk about some examples. So one of the opportunities is in the space of synthesis. How do you discover, relatively speaking, more by design, a class of materials that give rise to the functionality you seek? And that sort of comes in 2 domains. What's shown here are sort of various pictures of various kinds of architectures that have been built up from sort of the atomic scale up. And so the trick becomes, how do you do this not only using sort of atom by atom deposition techniques, where you're building those structures up from the bottom up by sort of putting atoms in their place, but also simultaneously doing that from the top down. How do you cause the system to assemble of its own volition and give rise to those structures? So how you create the structures is one of the synthetic challenges. And the other one is, how do you design materials that have a variety of functionalities? So consider a material that's not just electric or just magnetic or just having interelastic response, but does all those things simultaneously. And how do you discover those materials? Not by serendipity, by saying, well, let's try some stuff in this space, but let's make our sort of synthetic strategy a little bit more intentional by using a variety of tools to drive us to that place. And so that twofold challenge of how do you create the architectures and how do you realize that functionality much more intentionally than, say, people like me have done historically, where we say, well, my intuition says there's probably some interesting compound over here, and you go try some stuff, and you discover something, but it's not at all what you predicted, it's something else. And sometimes it's interesting, and sometimes it's not. There's much more intent in this approach to synthesis. Similarly, in the domain of measurement, we talked about that there are a variety of large-scale tools that you can use, and certainly LANSCE, that some of you saw yesterday, is one of those tools. We're not lacking for having large-scale tools to do science. What we're lacking is how to actually understand how materials evolve on these scales. So if the question is, I've got some mesoscale material that has some structure to it that includes defects and interfaces, and it's evolving in some way, say in response to some shock environment, and it's either behaving as you want or as you don't, how do you follow that in 3 dimensions, watching these things evolve across scales, while it's doing something interesting and sometimes nasty? That's a very different measurement challenge that's really important to think about. So there are a variety of efforts to develop tools in that regard, and that makes it an exciting opportunity. Sort of the curse of that excitement is that the volume of data you get is immense, because you're now not just measuring some particular materials quantity, but you're measuring what this spatial scale and this temporal scale, what's the quantity of interest in this environment. There's a huge challenge of understanding of all the stuff you could measure, what are the key ingredients to drive performance? And that opens up a broader challenge in that space as well. And so then the third of synthesis, characterization, and theory is the question of theory and scale. And so many people talk about multi-scale materials modeling. And in sort of almost any sort of material science talk you listen to, you can see plots that to a first approximation look like this, that say, across scales, from things that are very fast and atomistic to things that are very bulk and continuum scale, and across time, again, from things that are very atomistic to things that are very natural to us, there are these evolutions. And so that insight in and of itself isn't particularly unique. I think the thing to think about, though, is it's not just a question of how do you start at the bottom and work to the top, but rather, how do you work from the middle? How do you define this middle space as an opportunity that both builds on these insights and gives you leverage on these classes of problems where you may not necessarily have to, in order to understand these kinds of phenomena, you may not have to have atomistic understanding. It may be enough to have a partially complete understanding here. And so there's huge challenges in how you sort of connect theoretical understanding in that space, not just by sort of passing parameters from scale to scale, which opens up the problem significantly. So that's the character of the mesoscale science challenge. How one addresses those kinds of problems through a suite of theory, computation, experiment, and synthesis. And I think it's the case that as one looks at where the Department of Energy and especially the Office of Basic Engineering Science is going in the coming years, there will be a significant effort in this area. So that will be an area of materials research that will advance going forward. And so now what I want to switch the discussion to is how do we think about that in the context of NNSA? So at Los Alamos, we are very much active in sort of the Office of Science community, competing with, collaborating with all the other DOE laboratories, as well as the broader academic community. But we're also focused on delivering our mission. So the question becomes, as you think about the mesoscale science opportunity, what does that imply for the NNSA mission? What do we do about that? And so that's where I want to switch and begin to talk about this facility called MaRIE. But I want to start not by telling you what the facility is, but rather telling you why we think it's important and then get to the facility. Because if the why doesn't dominate the what, then there's no point in building such a facility. So as I've just tried to argue for you, materials research is really on the brink of a new era. This transition from observation and validation to prediction and control really is a central theme in where materials research is going in sort of the years to come. And that's driven by the kinds of advances we just talked about. Our ability to do things that we previously couldn't imagine really puts us at a tipping point for making big breakthroughs in this space. And nevertheless, the community, I think, recognizes there are a broad set of capabilities we don't have. That despite the opportunity, despite the promise, there are some gaps in the set of capabilities we have that will allow us to really make headway on this problem. And so the character of those gaps is the ability to make in-situ dynamic measurements. So this is measurements that are where the material is behaving as a function of time. So think not about before and after measurements, but rather during measurements. And so think about making movies, not just pictures sort of pre-mortem and post-mortem. And to do that, importantly, on materials that are well-controlled and well-characterized. It's sort of a depressing story, but Los Alamos has a long history of saying, here's a key issue. Let's separate the variables. Let's do A and let's do B, and we'll see the difference and we'll know the answer. And so we do that, and then we get surprised, and we say, well, wait a minute. We didn't quite know what A was or quite what B was, so we're not quite sure what the answer to the question is. So the ability to do these studies on well-controlled, well-characterized materials is essential. Our former director used to say that physicists used to do eloquent measurements on crummy materials, and material scientists would make elegant materials and do crummy measurements on them. Obviously, the opportunities to do elegant measurements on high-quality samples, and that's the goal here. For us, extreme environments are vitally important. That includes both dynamic extremes and irradiation extremes. And if you're going to be successful, you have to intimately couple the in-situ dynamic measurements of well-controlled and well-characterized materials in environments to modeling and simulation. So we think that's the grand challenge. We've worked very hard with the broader community to define that challenge. And quite deliberately, I've not said the word MaRIE to you yet, because this ought to be a challenge that the broader community understands and embraces. And in fact, that's the case. There are activities going on at the Advanced Photon Source at Argonne, at the LCLS at Stanford, at a variety of other labs and facilities that are trying to address these challenges. And for us, the particular instantiation that addresses these challenges is this facility called MaRIE. And as I'll describe, it very much builds on LANSCE, the facility that some of you saw yesterday, to take these advances to the next level. So if you think about the history of Los Alamos, LANSCE was sort of conceived in the 60s and 70s as a nuclear physics facility that's evolved into being, relatively speaking, a materials facility over the last 30 or 40 years. And LANSCE has played an essential role in defining both what Los Alamos is and, more importantly, who Los Alamos is. The number of people who came to Los Alamos through LANSCE is a very large fractional laboratory. While LANSCE is important to us, as we look to the decadal future, LANSCE doesn't quite get it done. And so MaRIE is our LANSCE for the next decades to come. And so I want to give you a flavor of what that science is. So in order to do that, it's worth sort of switching context a little bit and stopping thinking about, sort of from an Office of Science perspective, this question of observation and validation to one of prediction and control, and rather translate that to the specific challenges of NNSA. So what are the set of things that NNSA has to do? Well, in the space of materials, there's at least two broad things. One is we have to understand dynamic materials performance, how materials that are in our stockpile behave through the overall sequence that the stockpile experiences is very much central to our certification strategy. Our ability to have confidence that a weapon will work as designed in part depends very strongly on how dynamic materials perform and behave. So the translation of prediction and control, the prediction part very much maps to understanding dynamic materials performance. Of equal import, and I think this is the thing that's relatively new in recent years, is this question of control. The domain of process-aware manufacturing. So it's the case that the current stockpile was built over the last 10 or 20 or 50 years. And some of the ways we built it may not have been the most environmentally benign ways of building it. And some of the processes and parts we used just don't exist anymore. And so we have to rebuild and remanufacture a number of things. And the trick, without the ability to do underground testing, is to say, we're going to make it differently, and nonetheless, we have confidence that it will still perform. So a simple example of that is the plutonium cores in nuclear weapons used to be made at Rocky Flats up in Colorado. And the process that Rocky Flats used was they took the plutonium elements and they bent it into shape. So it's a wrought process. At Los Alamos, we now use a cast process. So rather than bending the metal into shape, we pour the metal into shape. From the point of view of materials manufacturing, changing from a wrought process to a cast process is not a huge and dramatic difference. It's basically the same material being formed in a different way. It took us of order a decade and of order $1 billion to have confidence that the cast product would behave similar enough to the wrought process. So on the one hand, that's an example of having a process-aware understanding of manufacturing. On the other hand, every time we make modest changes, if it takes us a decade and $1 billion to get it done, that's not very successful. And so that is very much the new part of the challenge, which is the part that's synonymous with control. So for the stockpile, we have to have a predictive understanding both of dynamic materials performance to reduce uncertainties in our models, as well as process-aware manufacturing to understand both how materials change as a function of time and predict how manufacturing changes make a difference. If we can do those things well, we can both deliver for the stockpile and do that for the broader set of challenges we face and have a workforce that enables us to be successful. And so that translation of prediction and control to dynamic materials performance process manufacturing is central to how do we sort of translate the broader materials challenge to core mission challenges for us. So if we sort of think about that carefully and ask, so what exactly is it that we can't do? It's what I just tried to describe to you. As we think about our future, we're concerned that we have an inability, that we have to have an ability to validate materials models across scales to build on other things we're doing. So if you can't do an underground test of the whole system, what do? Well, you try to deconstruct a problem and say, well, I can think about this part of it this way and explore it in these class of materials. I can't look at a whole system, but I can look at parts of a system. And if I construct that understanding together and connect it across scales, I can get to a predictive understanding. And those are gaps that we're trying to fill. Already talked about this question of developing process-aware materials models, both in order to address things we can't do anymore. Because whether we wanted to or not, there's no going back to Rocky Flats and saying, let's make our plutonium pits that way. So you've got to do it. But the more positive version is, it also opens up a huge range of possibilities. So a large part of how we think about qualifying materials today is driven by do it the way you've always done it. And if you want to have confidence that you do it the way you've always done it, what you end up with is a pile of paper that's about this thick that says, I'm copying exactly these steps that are 327 steps long in exactly the same order, changing exactly nothing. And when you say, well, that doesn't quite make sense, I think I could skip from step 13 to step 27 and save a bunch of time. We don't really have the ability to do that because our confidence is grounded in doing it exactly the way we've always done it. So there's both sort of the negative, you got to do it, but there's a huge opportunity in time and money to think about doing those things more carefully. And I think the most important reason, and in fact why programs like this are so important, is what we really need to do is train the next generation of stewards who will be doing this for the nation, doing these things for the nation, in the decades to come. So there are various plots of the age of weapons designers and both how old they are and how many that are still active have underground test experience. And I can assert two things. One, their average age is vastly larger than the average age of this room, and their number is shrinking dramatically. The country still needs that ability to steward the stockpile. Having been trained in how many underground tests you did is not what's going to be the commodity of the future. In the space of materials, it's the ability to do these things that is central. So it's in that context that we've thought about what we want to do as our future facility. And so, in fact, this is the question that Los Alamos has been thinking about for almost a decade now. So it turns out that back in sort of 2006, which was not one of sort of the brighter moments in Los Alamos' history, because we were having problems with various kinds of security incidents and losing hard disks and stuff. And it turned out that the core management of Los Alamos changed. So Los Alamos had been managed by the University of California from the Manhattan Project up until this period. And what the country decided was Los Alamos needed a different management structure. And so we could talk at length about that, but that's not so interesting. We made that change. And when Los Alamos changed its management structure, one of the things that the leadership laboratory concluded was we need to have a signature facility, a facility like LANSCE, that will serve us well into the decades to come that allow us to do national security science. And so having made that decision, the laboratory spent several years thinking about what it needed to do and what it wanted to be, frankly, when it grew up. And the conclusion that was made sort of on the time scale of 2008 or so was that focusing on this class of materials issues was the key challenge that faced the laboratory for decades to come. And so I got involved sort of around this period of time. And what we've done, which I think is important, is we've spent most of our time doing what I've been talking about of late. And that is, first, what is the question of the scientific need? What are the things you need to do? So define the problem, define the nail, before you think about what the hammer is that hits that nail. Because if you define a hammer first, I guarantee everything will look like a nail. But so you got to think about what the science need is and do that very broadly in the community. And then if you actually want to realize something, you need to define what that facility is. And so based on that scientific need, we defined a facility. And I think, interestingly, something that happened on this time scale is, our making noise about this, our thinking about what Los Alamos needs to be when it grows up, caused NNSA to think more broadly as well. So NNSA, in this overall period, decided that we, NNSA, more broadly, need to think about what our future facility footprint looks like. And so this actually led to a broader competition among Los Alamos and Livermore and Sandia for a set of future facilities that span the full range of the stock of the NNSA complex. And so that allowed us to translate this broader vision into a specific proposal that's happened to be called MaRIE 1.0. So MaRIE 1.0 is the least creative name you could think of for the first phase of a bigger thing called MaRIE. And I'll describe those details for you in a moment. So that's the overall history. And the fact that we translated science need to facility to an action proposal is the right order in which to do these things. And that causes us at the moment to be thinking about 3 Ps. So having written a proposal, it's pretty important that we're successful in that proposal. That's probably the least interesting part of all of this for you. I would assert there are 2 Ps that are relatively more interesting. One is MaRIE the project. So as I'll describe, MaRIE is a high-energy X-ray free electron laser that allows one to do multi-probe measurements simultaneously. There is very interesting science in how you build that kind of accelerator and how you do that kind of XFEL physics. We're investing significant money in retiring the risk associated with that project, including with a variety of partners like SLAC, which is where the LCLS is at, which is the world's leading XFEL today. And so one aspect of involvement, one aspect of places where we need to sort of grow future talent is in the technology to do this science. It's also the case that if the science is so important, you need to do that science today, even if you don't have all the tools you might want. And that's the 3rd P, and that's MaRIE program. And so we're investing significant money in dynamic material science in this space. And so both in MaRIE project and MaRIE program, we're actually doing work. We're doing science on a day-to-day basis, or we're also trying to move that proposal going forward. And so one choice is to say, well, let's wait and see if these guys are successful and come back in about a decade or so and then sign up to be a user. On the other hand, there's big room to get involved in this space, and that's the most interesting space of all. So let me define a bit what this facility looks like. So I told you that the focus was on in-situ dynamic measurements of well-controlled and well-characterized materials in extreme environments. So this is sort of a cartoon version of what you saw yesterday. So in this cartoon, in this direction, is the proton accelerator that you saw. It looks much older in real life than it looks in this cartoon, but nevertheless, it's a proton accelerator. And the idea is, let's take that proton accelerator, which is very useful for probing a set of materials using protons and neutrons, and build an X-ray free electron laser. Build an electron accelerator that converts those electrons into photons and allows you with high energy X-rays to study those materials. I'll tell you why you want to do that in a second. But bring those two beams together and have those beams interact in 3 measurement halls. A measurement hall focused on dynamic extremes, one focused on irradiation extremes, and one focused on the synthesis and characterization materials, which is also a dynamic environment. So if you have that multi-probe environment, you can study materials across a variety of spatial and temporal scales and understand how they behave. And if you want to understand materials at the mesoscale, and you want to understand materials that are relatively high Z, so we're talking about studying materials like tantalum and uranium and plutonium, and not studying things like carbon, it turns out that you need a relatively high energy X-ray source to penetrate those materials. So that taken together defines what the character of those probes are that you bring together in a variety of measurement halls. So that is the full description of MaRIE, understanding in a multi-probe way the ability to make movies, not before and after, in 3 different measurement halls. So that's MaRIE. So what about this 1.0 part? Well, so what we chose to do, because 1.0 is also not just sort of the first phase, it's also the approximate price. So it turns out that $1 billion is about the right price. So that's what 1.0 also stands for. Our first part is to build the multi-probe diagnostic hall. So imagine that you're doing some shock physics experiment. Imagine that you're using a laser driver or a high explosive driver to accelerate some material that's going to go through some behavior and go through a series of phase transitions. What you want to do is make a movie of how that behaves as a function of time, where your characteristic time scale is picoseconds to nanoseconds, and your characteristic length scale is microns or so. You can make a movie of how that material behaves in what's called the multi-probe diagnostic hall. We're going to defer the understanding of irradiation environments, which are very much important for the stockpile and are especially important for broader nuclear energy challenges, but we're not going to do that in the first instance. But the same measurement abilities you have here could directly be applied to here. And then finally, to address this question of well-characterized and well-controlled materials, we want to build a facility called M4, which stands for Making, Measuring, and Modeling Materials. That's 4 M's, to both give you samples that are well-characterized so you know what you're studying here. But more importantly, if you're going to make this transition from observation and validation to prediction and control, you've got to be designing materials here that profit from the insights you make here. And in fact, how you actually synthesize the materials, the temperatures and pressures to which you subject the material as it's being formed is a dynamic challenge as well. And if you're trying to control materials at the mesoscale, the same length scales and time scales you want to study as they perform affect how they're formed. And that's how the pieces come together. So that sort of is a quick version of MaRIE. And if you want to know more about the facility itself, I'd be delighted in some other context to talk at length about the various details of the facility. But what I want to close with is, again, come back to this question of theory, simulation, and computation, and this notion of co-design. And so part of that goes to the simple version of, if you're taking data that you can't possibly model, you're frankly wasting your time. And if you're modeling things for which there is no data, you're wasting your time in an even more troubling way. The good news is the time is right for something on this scale. And that comes in sort of 3 particular reasons. One is, and I apologize for this being a little bit small, if you think about how large of a simulation you can do, measured, for example, in how many atoms a simulation contains, and how long in time you can run these simulations out, where we are today is on the overlap between petascale computation and exascale computation. And if you translate those computer units into materials units, the kinds of phenomena you can access are very much the set of mesoscale challenges we're describing. So we're now able to make computations whose scale is large enough you can actually calculate from an ab initio way at the mesoscale. So you're now able to begin to be dangerous. The interesting question becomes, though, you can do better than that. What you want to do better than that is to say, how do I think about how the material is actually behaving? Because almost for sure, what you don't want to do is do a full atomistic calculation of a full continuum object. That will take you forever in computer time, and you're going to gather tons of information you just don't need. Rather, what you want to do is you want to decide what's the appropriate scale some phenomena matter. So the cartoon here is here's a shock wave, and it's propagating through this material. In parts of its time evolution, the continuum approximation is good enough. At other points in time, you have to recognize that it's a polycrystalline material and its polycrystalline structure matters. At more important points in time, the actual single crystalline atomistic physics matters. And so the trick is, how do you do that dynamically? So today what we do is we use techniques like adaptive mesh refinement. We dynamically decide how large is our computational grid, and we basically zoom in on regions of interest. The opportunity is to make a transition from adaptive mesh refinement, where you're just changing the size of your grid element, to what we'd call adaptive physics refinement. When do we turn on better and better models that understand, here's where the crack is actually forming. Let's use our very best models of how the crack forms and how phase transitions occur, and then sort of round that out at higher scales where it matters less. And so you're going beyond the ability to do the computation to choosing the right kind of physics where the models match the measurements to drive understanding. And if you're going to be successful for the stockpile, what you have to do is figure out what actually matters. Because you could make an infinitely good measurement of some material's property and have it not matter in the actual performance sense. And so the real opportunity is, how do you take these kinds of data and translate that to the integrated simulation codes that we run that at the most base level say, is the bomb going to work or not work? And applying that test of saying what matters and what doesn't matter actually sharpens your understanding of what you have to understand in terms of the underlying materials physics that moves you on just doing that computation. So there's a very real opportunity in having the specific mission challenge motivate what's actually important in this space and not just do it because you could do better, because that sort of is the easy way out. All right, so what are we doing in the near term? So here's a real picture of LANSCE that all you saw yesterday. LANSCE has been very important to us in terms of both sort of what our workforce looks like using a scientific tool. It's also given us significant experience in how to run a user facility. So our vision for MaRIE is very much as a user facility. Our vision is very much that people from all over the world come to use MaRIE to do the kind of science we're talking about with MaRIE, independent whether we work at Los Alamos or not. Those user facility challenges are non-trivial. It turns out that's something we do pretty well. It's also the case that implies we're going to do pretty classified experiments on things that are very important to us for the stockpile right next door to some academic user who's doing totally open science. And again, that's non-trivial, but we do that well. So our ability not only to operate the accelerator, but also operate the facility is important to us. You can ask the question, is there a user community? If you built such a facility, would they come? Are there people who actually think about these science questions? And the existence proof that the answer is yes is captured in all of these, which is sort of the cover art for the series of workshops we did in defining the opportunity. So the extent to which the community helps us define the opportunity says the people represented by the attendees here are the ones who become the user facility in that space. And most importantly is sort of the youngest third of this slide. And these are the set of people, these are a subset of the people working at Los Alamos today who will be our mid-career leaders when the facility comes to fruition. And so this is an example of how we're investing in the future. Again, not only using facilities like we have at Los Alamos, but also at Argonne and SLAC to foster that next generation. And so that's very much a space in which all of you can very much work as well. So I'll close by sort of reminding you what I told you about MaRIE in specific, but also about sort of mesoscale more broadly. There is a problem to be solved. This need to understand how materials behave in this scale is very key to our weapons challenges. As we think about where we have to be for stewarding the stockpile and national mission, this is an essential challenge. It's also a really cool material science. So if you want to do really cool material science focused on the stockpile, this is a good place to do it. We're happy that we've defined this facility in partnership with the community, because that means we probably got it right. And as I said before, you can sort of sit on the sidelines and wait till we get successful or not, or there are things to engage in now that move these things going forward. And that's an important, exciting part of where we're going in materials research. So with that, I'll stop, and I'll be happy to answer any questions, and I thank you very much for your attention.